today. So, okay, so we need to do, for our experiment, removal of various beam systematic modes. And so we do that using using a technique that we are dubbing, we're kind of naming this, deprojection. And what this does is we use a template map of the sky, actually the Planck 143 gigahertz map, basically at our frequency. We use that template map of the temperature sky to predict how those various beam systematics would enter into the time stream, into the time-ordered data of the various channels. And then we can calculate how that would enter for differential gain. That's just going to be temperature leading directly to polarization, so just a direct copy of the temperature. Differential pointing, where it's going to be the first derivative of that temperature map, and various higher order modes if we choose. And so we can calculate those templates for the various beam modes, and then we can essentially fit and subtract them from the data, thereby nullifying their effect on the data. Now, we can also do simulations where we inject the actual measured beam shapes, and then we check how well this works. Okay, so no deprojection to differential pointing deprojection, to differential pointing plus rel gain, and then the one that we actually do, which is this black line, which you can see is orders of magnitude down from the r equals 0.2 signal that we seem to be seeing. So we can not only do this deprojection, we can calibrate in simulation exactly how well it works, and we can know what the residual is that's left over and subtract that out of the end. Other systematics, so we've tried to imagine any possible systematic. You know, one can always challenge us, well, you didn't imagine well hard enough, but you know, we've done our best. So we have investigated many categories and classes of systematic and calculated based on internal information. In many cases, we can calculate an actual level. In some cases, we can only set upper limits, the dashed lines. And you can see that these are all well below the level that we care about. They're all smaller than R of 0.001. So very small compared to the signal that we're seeing. So, okay, so that's hopefully convinced you that the signal that we're seeing is real and on the sky, really comes from the celestial sphere. So then the question turns to, well, what is it? Okay, so it could be the primordial gravity wave that we're seeking, but one can also say, well, maybe it's foreground emission from the galaxy. So even though you're in this very low foreground emission region, perhaps it's not low enough, right? Perhaps you're still seeing galactic contamination. So we can project synchrotron for our field with pretty good confidence and pretty good accuracy using polarized maps made by the WMAP spacecraft at low frequencies. So we can project those up to 150 gigahertz observing frequency, and we can be pretty confident that that component is negligible. Now, polarized dust emission from our galaxy is more of a problem because good polarized dust maps at higher frequencies, like 350 gigahertz, do not exist yet. Well, actually, they do exist. The Planck collaboration happened, but they're not public yet. But nevertheless, we can use various existing models in the literature to project how much foreground we ought to be seeing from dust in our specific ultra-clean field. And we've done that. We've done a lot of work to try and do that. In fact, these DDM2 models that are shown here, these are using information from Planck. So using the DDM2 uses all of the available public information from Planck that we can get our hands on. And you can see that the DDM2 auto spectrum looks like it's, you know, possibly significant compared to our points, maybe 20% of the power level that we're seeing. But this is noise bias high. We also make a cross spectrum against that map. So if those foreground projections are actually real, they ought to cross correlate with what we're seeing. And if there is any cross correlation, it's weak. This cross correlation is consistent with 0. So you can't really read anything into it. So the basic takeaway point here is that all of the modeling that we can do predict that dust foreground in this particular field is very small, down at the R of 0.02, 0.04 kind of level, significantly smaller than the signal that we're seeing. Basically an order of magnitude smaller than the signal we're seeing on that order. So we can also get some information as to what this signal is by taking cross correlations against the maps from BICEP2. Now BICEP2 was less sensitive, was not able to see this signal on its own, but in cross correlation you kind of split the difference of the noise of the two instruments, and so you can get some guidance as to how bright the signal is at 100 gigahertz. So here, the solid points are the BICEP2 cross BICEP2, the auto spectra we've already seen. Then we have BICEP2 cross BICEP1 at 100 gigahertz, and BICEP2 cross BICEP1 at 150 gigahertz. This is really the important one, across at 100 gigahertz. And this is the only information that we have at other frequencies. And so, for these cross correlations are both consistent with the BICEP2 auto spectrum, and the cross with BICEP2 100 shows about a 3 sigma detection of excess power. Now, as has been emphasized, BICEP1 had very different technology. So if systematics were to be the cause of our signal, you'd certainly not expect them to be the same between the two instruments. So this is powerful additional evidence against systematics. You can also use the cross spectrum to set limits on the spectral index, the frequency spectral index of the signal that we're seeing. So if it was dust, then we would expect very little power at 100 gigahertz, and therefore very little power in the cross spectrum. If it was synchrotron, we would expect much higher signal at 100 gigahertz, and then therefore a very strong signal in the cross spectrum. So here is the spectral index constraint. Here's the maximum likelihood value. It's perfectly consistent with the expected CMB value, this line here, and moderately inconsistent with synchrotron or dust, at about 2 and a bit sigma in each case. So this is very powerful evidence that the signal that we're seeing, well, not very powerful, but powerful evidence that the signal that we're seeing is CMB in origin. It has this spectral index, the frequency spectral index expected for a thermal blackbody spectrum like the CMB. We can also take those cross spectra, we can combine the BICEP2 cross BICEP1 cross spectra, and here, even more interestingly, we're plotting preliminary cross spectra against our own Keck experiment, which has higher sensitivity, but is still in a somewhat preliminary state of analysis, and that's the blue asterisks here. And you can see that all of these cross spectra agree. So we're seeing the same signal in multiple different experiments. Powerful additional evidence against systematics. Okay, so now we get to the slide that you all want to see, right? So what constraint can we set on the tensor spectral index? On the tensor to scalar ratio R, this number that people have been, this mythical number that people have been questioning for a very long time. So we can take these data points, and now we can allow, so previously we were just showing an arbitrary R equals 0.2 model, but of course the reason that we're plotting that arbitrary model is because when we do the best fit, that's the value that we get. So now you add into the lens lambda CDM expectation the inflationary gravity wave template, the expected form of that signal, which has a specific form as a function of multipole number, and you look for the scaling on that template that gives the best fit. The value is R of 0.2. This is the likelihood curve now. The likelihood is a function of the R number. You can see it peaks at 0.2. The dashed lines here are showing you the region that contains 68% of the total likelihood. And then you can see it dropping down, and it drops very, very rapidly towards 0, right? Because these points are highly inconsistent with 0. Basically, as you scale up and down the R number, the error bars are also scaling up and down, because a lot of that is coming from sample variance, right? We've only measured a moderate number of modes on the sky, and so there's a lot of sample variance in there. An R value of 0.1 is allowed, 0.3 would also be allowed. If you go and measure a different patch of sky, you would get some number in this range. But what's important to note is that as you go down to 0, it's heavily, heavily disfavored by the data, and we get disfavoring of the R equals 0 hypothesis at 7 sigma. Right, shown right here. So that's the 5 sigma is how unlikely it would be to get our points given the null model. The 7 sigma is how unlikely it would be that that if R is really 0.2, you would actually measure R of 0. Okay, so we can take those foreground models that I just showed you, and we can subtract them out. We can arbitrarily subtract them out of our measured points, and then we can redo the R constraint. And if you do that, this is the family of curves that you get. You can see that DDM2 auto one, the one that I was asserting is little noise bias, that's the lowest, so we probably shouldn't take that one too seriously. The one that perhaps has the best chance of reflecting reality is the DDM2 cross, and that modifies the R number to 0.16 with a similar error bar, but R equals 0 is still ruled out at 5.9 sigma. So there really is no way to make the signal go away with dust, is the bottom line message. It just seems really, really unlikely. Okay, we can proceed to do a joint fit on these points, allowing now the lensing component to also scale. So now this is scaling the lensing component, where 1 is the standard value that it ought to take within lambda CDM. And you can see that there's some degeneracy. If you ask to fit between these two curves, this one and the gravitational wave template, you can explain some of this low L power by scaling up lensing. Nobody really believes that's the case, but it's kind of fun to let that float. We see that our data is perfectly compatible with the standard value. This is the range from Planck, right? So they've already constrained this parameter very well. We're really just constrained doing this for kicks. We end up with a 2.7 sigma detection of lensing B modes in the BB spectrum. So this is kind of a nice result, another kind of cutting-edge result. So now you can ask, okay, so you may have heard from Planck et al. Here are some previous limits that R has been constrained to be less than 0.11 at 95% confidence. And here I am standing here today telling you that it's 0.2. So how can this be, right? Well, first of all, we need to emphasize that there's a substantial sample variance error bar on our result. So R of 0.1 isn't that unlikely. But still, there seems to be a little tension between these results. So how could you relax that tension? Well, one thing that's in Planck's own paper, from where this plot is taken, the red contours here, they allow running. And so here they're plotting the scalar spectral index versus the R parameter, but there's a third hidden dimension, which is running. And if you allow running, their limit softens considerably, and it's no longer in any tension with ours. And here, the blue contours we've simply added to their likelihood chains. We've added our own data, and you can see that it prefers this value at about 0.2. There's really not a lot of tension if you allow running. Now, then people get, well, but they don't like the running value that perhaps that Planck is generating. So we're not advocating this as the solution, right? We're just saying, we're just observing that there are simple extensions to the lambda CDM model which would basically get rid of this tension between our data and theirs. And there are probably other possibilities within lambda CDM, and there are probably all sorts of exotic extensions to lambda CDM that could be dreamed up. And I invite all of the theorists out there to go ahead and do that. So just to summarize, so here we're showing again the upper limits, the previous upper limits on the B mode that John showed earlier, and now we're showing our data points fitting very beautifully to this gravitational wave component here, plus the standard lens lambda CDM component, and you can see that the points fit this joint spectrum very, very well. And there are now, or soon will be, plenty of points up here at the smaller angular scales measuring that lensing B mode further. So our power spectra are perfectly consistent with lambda CDM, except for this B mode, for this excess at 5 sigma, at multipoles around 80, exactly where the inflationary gravity wave is supposed to be. So we've done extensive systematic studies and jackknife tests, and they strongly argue against systematics as the origin of this signal. Foregrounds do not appear to be a large fraction of the signal. We've done foreground projections. We've asked if there's cross-correlation between our maps and the projected foreground maps. We've shown that the CMB, the spectral index of the signal is CMB-like, using cross-correlations against data from BICEP2 at 100 gigahertz. And you can just see from the shape of the B-mod spectrum that it just seems to fit this model really, really nicely. So ultimately, you end up with a constraint on R, ignoring foregrounds of 0.2 plus 0.07 minus 0.05, with R equals 0 ruled out at 7 sigma. As John mentioned, you can download all of the data from bicepkek.org, and we invite you to do so, and thank you for your attention.